Good day everyone, and welcome to where we are putting together solutions to those math and science problems that students are getting. In this video, we'll be looking at CSEC Mathematics, and specifically the topic of trigonometry, the question that comes in the second section of the past paper. We'll be looking at the past paper questions from May 2009 until 2013. Feel free to like the video and add any comments down below so we can help create other videos for you to assist in whatever areas that you are struggling with. Don't forget to look at the description down below where we have outlined the order we suggest for the entire Maths CSEC syllabus so you can get a better grasp of the entire topic. Let's look at the 10 major topics in CSEC Mathematics, and in this video we'll be looking at topic number 8, Geometry and Trigonometry. This topic is tested for 8 questions out of the 60 in paper 1, multiple choice, and for 21 marks in paper 2, which is worth 2 full questions. This topic can be subdivided into 2 parts, into geometry or trigonometry. In this video, we'll be looking at trigonometry, so that itself can be subdivided into right angle triangles or any other triangle. Within right angle triangles, we specifically look at that diagram above where we give the angle, the hypotenuse h, the opposite o, and the adjacent a. And the rules that relate them, we can relate the lengths of all 3 sides using Pythagoras' theorem, which states o squared plus a squared is equal to h squared. Or we can use trigonometric ratios, sine theta is equal to o over h, cos theta is equal to a over h, and tan theta is equal to O over A. Those 4 work for any right angle triangles. And for any triangles, whether they are right angle or not, we can use the sine rule, A over sine A is equal to B over sine B, which is equal to C over sine C. Or we can use the cosine rule, A squared is equal to B squared plus C squared minus 2BC cos A. This topic came 6 times in the 5 years, twice in May 2009, and then the paper changed so that it came only once every other year. Let's look at some basic steps we can follow if we're getting problems with this topic. When tackling this topic, the first thing we can do is list all formulae, which are 4 formulas for the right angle triangles and 2 more if it's considered for any other triangle. Then we identify which shape is relevant. We redraw only that shape. And then we identify which sides and angles the question uses. Select the formula, substitute, and then solve. May 2009, number 11b. The diagram below, not drawn to scale, shows the position of 2 hurricane tracking stations, P and Q, relative to a point O. P is on a bearing of 25 degrees from O, and OP is equal to 400 kilometers. Q is on a bearing of 80 degrees from P, and PQ is equal to 700 kilometers. So the diagram we're looking at on the right hand side, that's what was given in the exam. Part 1. Copy the diagram above. On the diagram, label the angles that show the bearings of 25 degrees and 80 degrees. So, let's go back to the information. 25 degrees was the angle from O. So if we stood at O and we're facing north, and we turn clockwise to the right, then that will be shown in a red arrow. And how much degrees? 0.25. When we're writing these angles, we always use 3 figures. And 80 degrees would be standing at P, facing north and turning clockwise until we face Q. Part 2. Calculate A, angle OPQ. So if we extract angle OPQ, so let's bring it up. And if we extract that, look, we see angle OPQ, that large angle there, we have in a dotted line. And let's see if we could break that up into parts. First of all, we know that angle on the left side, which is 25 degrees. And we have 2 parallel lines. So let's draw this in black, and we can see that shape shows us that that angle in black is the same as the angle in red. And why is that? Because alternate angles are equal. So the 25 degrees will be the same for the red angle and 25 degrees for the black angle. And can we get the other part? So we got part of angle OPQ, which was 25 degrees. We need the next part now. And we know that the bearing was 80 degrees. And that north line there, 180 degrees. So if we know 80 degrees above, what's in green? What's the remainder? 100 degrees. As such, the angle OPQ is 25 degrees plus 100 degrees, which is 125 degrees. So we found angle OPQ. Part B, calculate the length to the nearest kilometer of OQ. So let's show you with that purple arrow where OQ is. And let's bring up certain information that we know. We know 400 kilometers is OP. We know PQ, which is 700 kilometers. And we know 125 degrees. Three things. And we want to find this line OQ. So if we're considering only one angle and three sides, that is using the cosine rule will help us. So let's write that. A squared is equal to B squared plus C squared minus 2BC cos A. And if we identify where the angle is at P. In our formula, we can substitute A as P. And we'll have OQ squared is equal to OP squared plus PQ squared, those sides, minus 2 times OP PQ cos P. And we substitute 400 squared plus 700 squared minus 2 times 400 times 700 cos 125. Let's substitute that into our calculator, and it will give us 971,216. That's OQ squared. So if we want OQ, we carry the square across, we'll get square root, and OQ is equal to 985.5 kilometers. Part C of the question, calculate the bearing of Q from O. So let's bring that up as a purple arrow, and of course the bearing means that we're standing at O, facing north, and we're turning in a clockwise direction. That's what the purple arrow indicates until we face Q. So they want us to actually give them the entire angle NOQ. And we can break that up into parts. We already have NOP, and POQ will give us our answer. NOP is equal to 25 degrees. So we only need to solve for POQ, the angle inside there, and it will help solve the question. So let's extract that triangle, and if we extract it, let's bring up in red the angle that we're looking for, the angle inside of the triangle. And what do we know? We know 400 kilometers, we know 700 kilometers, we know 985.5 kilometers, and we know 125 degrees. So if we want to find an angle, there are a couple different ways we can use it. We can use the cosine rule, or we can use the sine rule. Both ways will help solve the question. So I already did the cosine rule in the first part of the question, so let's use the sine rule here. O on sine O is equal to P on sine P. We want to find an angle, so let's reciprocate both sides or flip it. So we get sine O, which is, and O is really sine POQ, that angle, over what is O? What is the length of the opposite side of O? That's PQ, is equal to sine P over OQ. And sine POQ over 700, as we substitute, is equal to sine 125 over 985.5. And if I want sine POQ, we carry the 700 across, it's dividing, it'll multiply when you carry it across, you'll get 700 times sine 125 all over 985.5. And we substitute into our calculator, we're going to get 0.582. So if you want the angle POQ, then we carry the sine across. The sine, when we carry it across, will be arc sine or sine inverse, 0.582. And that works out to be 35 degrees using our calculator. So we can now substitute. So we get 25 degrees plus 35 degrees. As such, the bearing is 60 degrees. or 060. May 2009, number 12. In this question, use pi as 22/7 and assume that the Earth is a sphere of radius 6,370 kilometers. The diagram, not drawn to scale, shows a sketch of the Earth with the north and south poles labeled N and S respectively. Arcs representing circles of longitude 35 degrees east and 15 degrees west, and circles of latitude 0 degrees and 60 degrees north are drawn, but not labeled. A. Copy the sketch and, part 1, label the arc which represents 60 degrees north. So, if it's a line of latitude, it means it's a flat line or horizontal one. So we have two horizontal lines. The middle line will be the equator, which is at 0 degrees, and the higher one is 60 degrees north. And B, also labeled 35 degrees east. So we have two lines of longitude there, and the one to the east will be the one on the right side. Insert the points J, which is at 60 degrees north, 35 degrees east. So let's look at the intersection of the 60 degrees north, that arc that we had, and the 35 degrees east, and that point is J. And for part B, insert K, 60 degrees north and 15 degrees west. So it will still be on that horizontal arc, but it will be to the left. Part B, calculate to the nearest kilometer the shortest distance from part 1, J to the North Pole measured along the common circle of longitude. So what we could recognize here, let's bring up that line, we'll highlight it in yellow or orange, from J going up to N, and that is part of a circle whose radius is the radius of the Earth. If we want to find the length of an arc along a circle, then the length of an arc, let's represent that as S, from J to N would be the angle that we're moving, theta, over 360 degrees, that fraction, multiplied by 2 pi r, r being the radius of the Earth. So let's substitute. What is the angle? The angle was from 60 degrees and we went up to 90 degrees, 90 degrees being the North Pole. So 90 minus 60, all over 360, multiplied by 2 times 22/7 times the radius of the Earth, 6,370 kilometers. And if we put that into our calculator, that gives us 3,337 kilometers. May 2009, number 12, part B. Calculate to the nearest kilometer the shortest distance from, and this is the last part of the question, part 2, J to K, measured along the common circle of latitude. So, if we look at our diagram, let's draw a line from J to K as if we are walking on the surface of the Earth, and that will give us our shortest distance. So let's bring up a circle and let's extract it as if it is not a 3D shape but a flat shape. And let's draw our equator as a black line in the center, and let's use the radius of the Earth in red, and let's rotate it 60 degrees upwards. And why are we going to use 60 degrees? Because that is going to give us our 60 degrees north line. As we've drawn the diameter at the 60 degree north line, let's compare the angle that we have in red and the one up above in green. What can we tell? We have two parallel lines in black cut by a transversal in red. And if we're comparing the red and green angles, we can say those angles are alternate angles. And what's the ruling? Alternate angles are equal. So therefore the green angle up on top is also 60 degrees. Now let's draw from the center of the Earth upwards a green line, which means that it's forming a 90 degree with R60, the radius at 60. So we've now gotten a right angle triangle. and we know an angle, we know it's 90 degrees, and we know the radius of the earth. So can we find the radius at 60? We can do that because we have the adjacent and we have the hypotenuse. So we can use cos theta, that trigonometric ratio. Cos theta is equal to adjacent over hypotenuse, and if we substitute, cos 60 is equal to, what's the adjacent? R60 over the radius of the earth. And we know the value for the radius of the earth, so let's substitute that. Cos 60 is equal to R60 over 6,370. And if we want R60 alone, we carry the 6,370 across, so it will multiply, and that will give us 3,185 kilometers. Now that we know that, can we now look at that circle from above? And if we recognize that 60-degree north circle, the Arctic circle, then what we're doing when we're finding distance from J to K is we're finding the length of an arc. And the formula for length of an arc will be a fraction of the circumference of a circle. So it will be theta over 360 multiplied by 2 pi r. R being the radius of 60. And if we substitute, what's the angle? We're at 35 degrees east. That means 35 degrees to the right of the GMT, of the 0-degree line. And we're moving to K, which is 15 degrees west. So that will give us 15 plus 35 all over 360 multiplied by 2 multiplied by what's pi? 22 over 7 multiplied by R60, which we worked out in the first part. Put that into our calculators. That will give us the final answer, 2,781 kilometers, which is the distance to move from J to K. May 2010, number 10b. The diagram below, not drawn to scale, shows a vertical flagpole, FT, with its foot, F, on the horizontal plane, EFG. ET and GT are wires which support the flagpole in its position. The angle of elevation of T from G is 55 degrees. EF is equal to 8 meters, FG is equal to 6 meters, and angle EFG, which is flat on the ground, is 120 degrees. Calculate giving your answer correct to 3 significant figures. Part 1. The height FT of the flagpole. So if we look at the diagram, we can see that there are 3 different triangles, and only 2 of them deal with FT, the one on the left side, EFT, and the one on the right side, GFT. So which one can we use to help solve for FT? Well, we know 2 pieces of information on the one on the right side. We know 6 meters and 55 degrees, so let's extract that. And recall that FG is flat on the ground, FT is vertical, so there's an angle of 90 degrees between it. And if we have a 90-degree triangle, we'll be using one of the 4 rules, either Pythagoras' theorem, sine theta, cos theta, or tan theta. And we want to find FT. FT is the opposite. And we know FG, which is the adjacent. So opposite and adjacent means we're going to use the tan rule. So tan theta is equal to O over A. And let's substitute. Tan 55, remember, make sure your calculator is in degrees, is equal to, what is the opposite? FT, all over 6. And if you want FT alone, we get rid of the 6 on the right-hand side. It's dividing. It's in the denominator. When you carry it across, it will multiply. So it will be 6 tan 55. The multiplication is understood. And if we put that in our calculators, we're going to get 8.5688, continuing, which is FT. But we want our answer to 3 significant figures. So if you notice, the third significant figure is 6. So I've put that in a different color so you can identify it. And if we're rounding off the 3 significant figures, we look at the number to the right of it, which is 8. 8 is a large number, or 5 or more. So we don't remain as 8.56, but we change it to 8.57 meters. That's approximately the height of FT. Let's bring up 8.57 on the diagram. Part 2. Calculate the length of EG. And if we look at EG, and that triangle that is connected with, that's the base triangle EFG. So let's extract that. And what do we know? We know the left-hand side, EF, is 8 meters, the one on the right side is 6 meters, and the angle is 120 degrees. So we have two sides and we want to get a third side, we have an angle. So we're going to use the cosine rule. A squared is equal to B squared plus C squared minus 2BC cos A. So let's substitute. EG squared is equal to EF squared plus FG squared minus 2EF FG cos F. And if we put in the values that we know, 8 squared plus 6 squared minus 2 times 8 times 6 cos 120. If we put that into our calculators, we're going to get 148 degrees. So EG is the square root of 148 degrees, which is 12.165 meters. But we want our answer to three significant figures. So the most significant figure is 1. Second most significant figure is 2, because we start on the left-hand side with the first non-zero number. The third most significant figure is 1. And we have that in red. So are we going to write 12.1 or going to 12.2? Well, we look at the number after the 1, that's a 6, so it means we increase it. So EG, that length is approximately 12.2 meters. And for the last part of the question, part 3, the angle of elevation of T from E. So if we're looking at that angle, that's on the left-hand side, then we need to use that triangle. Let's recall that as we extract the triangle, EF is on the ground, FT is vertical, the height of the flagpole, which we knew as 8.57 meters, and we want to find that angle. We're bringing it up in red. Notice it's an angle of elevation, which means it starts on the ground and is going upward, so we have an arrow on it. Please put an arrow on yours. And how do we find that angle? We know the opposite, 8.57, and we know the base, the adjacent, which is 8 meters. And if we have O and A, then we'll be using the rule tan theta is equal to O over A. Let's substitute. Tan of that angle, FET, which is what we want to find, is equal to FT, that height, over EF. So tan FET is equal to 8.57 over 8. And if we carry the tan across, we get arctan, or tan inverse, 8.57 over 8. Put that in the calculators, we're going to get 46.97 degrees. And we want to get it to three significant figures. So again, I put the third one in a maroon color so you can see. Do we mean as 46.9 or do we increase it? Well, the number after is 7, so that means we're going to increase it. 46.9, if we add 0.1 to that, we get 47.0. It's important to put three numbers here to show it's three significant figures. May 2011, number 10b. The diagram below, not drawn to scale, shows the route of an aeroplane flying from Port City, P, to Queenstown, Q, and then to Riverdale, R. The bearing of Q from P is 132 degrees, and the angle PQR is 56 degrees. Part 1. Calculate the value of x as shown in the diagram. So if we look at the diagram, and let's look for x, that's on that north line. So let's extract it. And what do we know? We know the north line is a straight line. So that add up the three angles, and it's going to give us 180 degrees. Substitute 48 plus 56 plus x is equal to 180 degrees. 104 plus x is equal to 180 degrees. If you want x alone, carry the 104 across. So it'll be x is equal to 180 minus 104. So x is equal to 76 degrees. And for part 2, the distance from Port City to Queenstown, Q, is 220 kilometers. So let's bring that up. And the distance from Queenstown to Riverdale is 360 kilometers. So let's bring that up. Calculate the distance RP. So if we take a look at that, let's extract that triangle. And what do we know? We know the angle is 56 degrees. We know we want to find RP. And we have those two sides, 220 and 360 kilometers. So if we're dealing with three sides and one angle, that's the cosine rule. So let's write that. A squared is equal to B squared plus C squared minus 2BC cos A. And that's given on your formula sheet. And if we substitute for, if we know the angle is 56, that's Q, then we're using the side opposite to that. So RP squared is equal to PQ squared plus QR squared minus 2PQ times QR times cos Q. And if we substitute the values, 220 degrees plus 360 degrees minus 2 times 220 times 360 times cos 56. RP squared is equal to 89,296 according to our calculators. And if you want RP, then we get the square root of that, which is 299 kilometers. Part 3 of the question, determine the bearing of R from P. So let's consider standing at P, facing north, and turning in a clockwise direction. We already have the first part, which was given as 132 degrees, NPQ, and keep turning until we face R. So that includes a green part that we have there. And we put a clockwise arrow on it to show the direction of the turning. So the bearing would be angle NPQ plus angle QPR, and that would give us our entire bearing. Now we already know 132 degrees is NPQ, so we need to work out the part in green. And let's extract that triangle so we can see it. And what do we have? We have 299 kilometers, and that's opposite 56 degrees, and we have 360 kilometers. And what that means, the angles and their opposite sides are there's a correlation between them, so that if the angle is bigger, then you're going to get a bigger side. So we have 360 kilometers, means that our angle should be more than 56 degrees. So we're going to use our sine rule, as we have two angles. P over sine P is equal to Q over sine Q. And we want to find the angle, so to make the math a little simpler, we can flip both sides, get the reciprocal. So sine P over P is equal to sine Q over Q. And let's substitute what we know. Sine P over 360 is equal to sine 56 over 299. If we want sine P, carry the 360 across, so it will be 360 times sine 56 all over 299. Sine P is equal to 0.998 according to our calculators. So if you want to find P, carry the sign across, make sure our calculators are in degrees. So sine inverse or arc sine 0.998 is equal to 86 degrees. As such, we can substitute that. So it will be 132 degrees plus 86 degrees. Our bearing of R from P is 218 degrees. May 2012, number 10A. The diagram below, not drawn to scale, shows a quadrilateral QRST, in which QS is equal to 7 centimeters, ST is equal to 10 centimeters, QT is equal to 8 centimeters, angle SRQ is equal to 60 degrees, and angle RQS is equal to 48 degrees, all of which is shown on the diagram. Calculate, part 1, the length of RS. So if we look at RS, that's actually dealing with the triangle on the left-hand side. So let's extract that triangle, and we have two angles on one side, and we want to find the other side. So the best rule to use there would be the sine rule, and Q over sine Q is equal to R over sine R, and we can substitute what is actually that Q, the length RS, over sine 48 is equal to 7 over sine 60. So if you want RS, we can carry the sine 48 across. It's dividing on the left side. When you carry it across, it will multiply. Sine 48 times 7, or you could put 7 sine 48 all over sine 60, and that gives us 6 centimeters. Part 2. Calculate the measure of angle QTS. So if we look at QTS, that will be the triangle on the right-hand side. And if we want to find that angle, let's extract it first so you can see it easier. And let's bring up that angle in green. And what do we know? We know 8 cm, 7 cm, and 10 cm. So we know three sides, and we want to find an angle. So we can use the cosine rule. So a squared is equal to b squared plus c squared minus 2bc cos a. And we can substitute where what we're calling as the angle A is really, according to this diagram here, the angle T. So if we substitute, we get t squared is equal to q squared plus s squared minus 2qs cos t. And we know, let's put in the values. Let's substitute. 7 squared is equal to 8 squared plus 10 squared minus 2 times 8 times 10 cos t. 49 is equal to 8 8s are 64 plus 10 10s are 100. So that's 164 minus 2 by 8 is 16 by 10 is 160 cos t. And if you want to find cos t, we carry across the 164 first. It's adding on the right hand side. When you carry it across, it will subtract. So we get 49 minus 164 is equal to minus 160 cos t. And that works out to be minus 115 is equal to minus 160 cos t. So if I want cos t alone, let's carry across the minus 160. They are multiplying. When I carry it across, it will divide, or multiplicative inverse. So we're going to get minus 115 over minus 160 is equal to cos t. So if I want t alone, carry the cos across. The opposite of cos will be arc cos or inverse cos or cos inverse. Different ways of saying the same thing. Cos inverse minus 115 over minus 160, and that works out to be 44 degrees. Just make sure that your calculator are set in degrees. May 2013, number 10b, the diagram, not drawn to scale, shows 3 points R, S, and F on the horizontal ground. FT is a vertical tower of height 25 meters. The angle of elevation of the top of the tower T from R is 27 degrees. R is due east of F, and S is due south of F. SF is equal to 43.3 meters. Part 1. Sketch separate diagrams of the triangles RFT, TFS, and SFR. Mark on each diagram the given measures of sides and angles. So, let's look at the first triangle RFT. That's the triangle that looks like it's standing up. And let's extract it. And what's the information? 25 meters was the height of the vertical pole, which is we have on the diagram, and also the angle of elevation of the top of the tower from R. So that means if we're standing at R, we're looking horizontally across at F, and we're turning our heads up until we see T. That means that the angle we're drawing should have an arrow on it indicating that it's going upwards, because it's an angle of elevation. And how much is it? 27 degrees. For the next triangle, TFS, that triangle will still have TF as 25 meters and FS is 43.3 meters. And what do we know? That FS was on the horizontal ground and TF is a vertical tower, so the angle between them is 90 degrees. So in the first diagram, we have two bits of information and a right angle triangle, so we can find anything else, any other angle at any other side. And the same thing in the second triangle, because we have two bits of information and it's a right angle triangle. And for the third diagram, SFR, if we look at it, it lies flat on the ground, but FS goes in an easterly direction and F to S is a southerly direction. So it means that there's also 90 degrees between them, and we have 43.3 meters. For part 2 of the question, show by calculation that RF is equal to 49.1 meters. If we look at the triangles on the left-hand side, which one of the three should be picked? We want to find RF. So the triangle on the extreme left does not even have R in it, so we can't use that. So it'll either be one of the two on the right-hand side. Now, if we look at the lower triangle, apart from being a right angle, we only have one piece of information. So it's insufficient to use that. But if we use the first triangle we drew, triangle RFT, we have two bits of information. We have an angle and we have 25 meters, which is the opposite. And we want to find RF, which is the adjacent. So if we have O and A, we can use tan theta is equal to opposite over adjacent. And we can substitute because out of those three things in the formula, we know two of them. Tan 27 is equal to 25 over RF. RF is in the denominator, it's dividing. When we carry it across, it will multiply. So we'll get RF is times tan 27 is equal to 25. And if we want RF alone, we can bring tan 27 down below, so we get 25 over tan 27. For some of you who seeing it quicker, can skip this third line. And when we use our calculators, we're going to get 49.1 meters. So we've proven what they ask us. For part 3 of the question, calculate the length of SR, correct to 1 decimal place. So if we look at our shape on the right hand side, and we're looking to find SR, that is in the triangle on the base, on triangle SFR. So let's just redraw that and put in the information we know. We know 43.3 meters, and we've proven that RF was 49.1 meters in part 2. So if we have those two pieces of information, we have two lengths. Can we find the third length? Because it's a right angle triangle, we can, and we'll be using Pythagoras' theorem. So let's write that. O squared plus A squared is equal to H squared. And it doesn't matter in this case, the angle is not necessary, so it doesn't matter which one of the short sides we consider as O and A. They're interchangeable. So let's substitute. 43.3 squared plus 49.1 squared is equal to H, the hypotenuse, the longest side, SR squared. And let's use our calculators, and that will give us 3,564.1 is equal to SR squared. So if we want to find SR, let's carry the square across, and the inverse of square is square root. So the square root of 3,564.1 is 59.7 meters. And does this answer make sense? Well, let's look at the two values we had for the two lengths. 59.7 is longer than either one of those. And that is what it's supposed to be. The hypotenuse is supposed to be the longest of the three sides in a right angle triangle. For the last part of the question, part 4, calculate the angle of elevation of the top of the tower T from S. So if we want to involve T and S into our triangle, then it will be the triangle that we did on the left hand side in part 1, which was TFS. And as we bring it up there, what do we know? We know the 43.3 meters on the base. We know the 25 meters is the vertical height of the tower. And we're asking to find the angle of elevation. So if we're at S, first of all, we look horizontally or flat, and that will be S looking at F. And then we'll be turning our head slowly upwards until we see T, the top of the tower. So when we're drawing our angle, which we have in red there, we put an arrow upwards, showing that's an angle of elevation. If it was depression, then our angle will be going downwards. And how do we get that? Look at the information we know in this right angle triangle. We know the opposite, O, and we know the adjacent, A. So the trigonometric ratio we should use would be tan theta is equal to O over A. And let's substitute tan S, which is the angle that we want to find, is equal to 25 over 43.3. And if you want to carry the tan across, so that we're left with S alone, S is equal to the inverse tan, or arctan, or tan inverse, 25 over 43.3. And that gives us 30 degrees. We've now come to the end of CSEC past paper questions in the topic of trigonometry that comes in section 2 of the paper. In this video, we've done past paper solutions for 5 years from May 2009 until 2013. In our next video, we'll be doing the next 5 years from 2014 until 2018. Feel free to look at the description down below to give an overview of the entire CSEC Maths syllabus and the order we suggest that you go through it to get the best understanding of the subject area.